Katerina, can you hear me?
So, um, Irish oatmeal.
Dr. Spontak, hello again. How are you?
Hello, Jamie. Nice to hear your voice. How are you?
Very, I'm doing very well, thank you. You've been well, and how's your dogs?
Um, the dogs are doing okay, but my wife and I have had COVID.
Oh no.
Yep. In fact, I didn't take my test this morning, but as of yesterday, as I will be pointing out in my talk, I still tested positive yesterday.
I'm so sorry to hear that. And we're very grateful you're still here, actually. That's incredible. Thank you.
Well, it's kind of interesting because I gave a more detailed version of this talk at a conference earlier this week, and yeah, when they asked me, how are things going, and I told them I had COVID, they were like, "What? And you're still giving a talk?" It's like, yeah, that's what we academics do, neither rain nor sleet nor snow.
Science Society salutes you for this. Thank you.
So I momentarily heard Katerina, but it was very, very choppy. You're actually quite clear. Am I clear for you?
Very, yes, very clear.
Good.
But we don't have any feedback remember the problems last time when you had to wear the headset around your ear, your
Oh,
neck and things?
yeah. I think I figured out what happened. Um, I think it was the fact that my new headphones were causing feedback with uh, the output from the computer, and so this time I made sure that they're not only turned off, but they are in a room on the other side of the house in case they somehow want to get activated again. So, so I don't think
That
there should be a problem.
Good, good. But you're able to wear them today and hear everything properly, which is the big thing because you were doing really well before. You had to juggle around, right? You had to put the headphones on and mute yourself to hear a question, and then you
Yeah.
had to
Oh, yeah.
just.
That was quite interesting. Excuse me.
But you're a dab hand at it now.
Could
You're a oh, hi Katrina, you're in the
you
matrix.
hear me? I am.
Good
We can.
morning.
Let me try again. I see.
It's breaking up super bad, Katrina. You're in the matrix.
I was wondering what that illusion was.
Is it is it better now? My red bar is gone. Is it
That's
because
much better.
It's
yes?
better.
Okay, oh, perfect. Yeah, I'm sorry. I'm on vacation this week, so my internet is, depending on, I don't know, the weather. I don't know. But but yeah, thank you so much for making it, Rich. I hope you feel better at least, although you test positive. I hope you're
I,
feeling
I
better
feel
by now.
much better than I did last week. Last week was hell. This week, I'm able to work and I don't have as much brain fog. Although, when I make a mistake now, it's so nice to be able to just blame it on COVID.
Yeah,
Given your
me.
position, that must be a relief. Sorry. Yeah, please, Katrina.
No, no, go ahead. Sorry. I wanted to say, we go through it, so we should take advantage also.
So where are you on holiday right now?
Uh, Actually, so my family is visiting, after years not seeing them because they're also in Europe. They are visiting, so we went this week to the Hamptons. I'm showing
Hmm.
them around a little bit, and next week will be for a few days on Rhode Island, and then they are already going back again. So,
Oh, wow. Okay.
yeah, it's in the city. It's crazy hot. Like, uh, it's like really warm, and it's yeah, it's almost unbearable to do things unless you're like in a museum. But they also don't want to get COVID to be able to go back. So,
Yeah.
outdoor things are better.
Well, I don't know if you had seen the article that posted yesterday about how Nice, France is now requiring people to wear masks again on public transportation. And my wife and I looked at that and we just laughed because that's where we got COVID, in Nice. And I think
Oh wow, yeah.
we were the only ones wearing masks on public transportation and in crowds. I mean, we were trying to be protected, but still, it wasn't sufficient.
Oh no, that's not very nice.
I was waiting
Sorry,
for it. I
sorry,
really
sorry,
was.
sorry. That was my one a day. I apologize.
Oh, don't I like it? Uh,
But it's frustrating when you're the one that was masking up and you still managed to catch it as well. It's yeah,
yeah, I mean,
frustrating.
the masks can only do so much. So
Mhm.
it really it's a full team effort. If you're the only ones wearing masks, I mean, you're probably still going to pick it up as we demonstrated. But yeah, people just need to realize that it's very dependent on the concentration of particles in the air. And if people aren't wearing masks, they are literally polluting the air.
Hey, Dr.
So,
Spontak, maybe you could work in some kind of like large polymer suit that we all completely wear that covers us completely from COVID. Maybe that could be your
uh,
next thing.
that already exists. In fact, I have one sitting in my office, right about uh, 15 feet from where I'm sitting. Yeah, I actually have one.
Really?
I bought it. It's basically a pseudo or quasi isolation suit. It's not the same type that you would see at biosafety labs, for example, where they're getting oxygen input from an external tank or an external pumped source. But there certainly is, an opportunity to be somewhat isolated. So the suit I have actually has fans built into it to maintain a higher positive pressure inside the suit so that particles cannot come into the suit. And it has membranes all over the place. So yeah, it does exist. In fact, I got the idea from Qantas Airlines because at the beginning of the COVID pandemic, in their first class, they were handing out these, the type of suit that would basically just come down to your chest, but it would essentially isolate your head, which of course is where most of the respiratory issues, of course, arise. Um, so yeah, those types of suits exist, and the one I got, it wasn't that expensive. It was about $600, um, and of course, it was manufactured overseas, which meant that it took a very long time for it to actually come to the U.S.
And is that one of those things? I don't know anything about these suits, but do they have like levels to them then? Like one of them would help against the general things, another stronger one would help against radiation. Do they have their
No,
like
no, no,
levels
no.
like that?
No, this is strictly against microbes. Strictly against microbes. So
Oh, okay.
no, this one doesn't protect against anything else. So no, I haven't gone the Tony Stark route.
Oh no. That would be so cool. But well, you need something to do tomorrow, Doctor, right? You know.
This is true. This is true. Uh,
And I
sorry
have been looking.
if
Sorry,
I'm
please
coughing,
continue.
sniffling a little bit, but the congestion is still hanging around. I can't get rid of it.
No, not a problem. You just relax and take your time. We're here to listen. And I've been reading your paper, and I guess what? I have a few questions for you as well. So,
Excellent. I love questions. Were
um,
you able to get the slides okay?
um, Katerina?
Were you able to get the slides that I had sent to Katerina?
Yeah,
Yes,
I'm gonna
we
just
have the
get
slides
your.
and I'm putting them up right now.
Ah, great.
I think earlier it didn't work when I was in.
Ah,
Okay,
there you go.
can you? There.
Yep, yep. It's
Okay,
in.
now it works. Yeah, we're starting in around 4 minutes. Thank you everyone for coming, and of course, special thanks to you, Rich, for this presentation. Um, is really cool. I think everyone will enjoy it a lot. I had the chance to take a peek at it. So yeah, it will be very exciting. And hi Frank, how are you? Hi Gilbert, how are you guys doing today?
Hello, Karina. Hello,
Hey.
Rich. Welcome to the Science Society. Looking forward to your sharing.
Thank you so much. Appreciate it.
For you it's late right now, isn't it, Frank? I don't know what time it is for you right now.
It's late, but it's okay. It's a pretty good time. Yeah, it's
Where are you located, Frank?
I'm in the Hong Kong and Beijing time zone, the eastern part of China. Yeah.
Okay. Yeah, so this is a little bit late, not too bad. I actually had to give a talk to the Society of Polymer Science Japan a couple weeks ago, and my talk started later than this. So late for me, early in the morning for them. So yeah, I appreciate you staying with us this late.
Not at all. This really great honor and pleasure to be able to audit your lecture. So, yeah. So regarding the time zone, it especially during the COVID years, it's fine. It's almost it's like how to court and become math prize problem, right? How many time zones can you maximum accommodate in one Zoom meeting, right?
Yeah, I actually have been in some Zoom meetings where um, I would say New Zealand, Australia, China slash Japan slash Korea, and then there were several people from Turkey and Iran, and then of course people from Eastern Europe and Western Europe and London. So yeah, there was a good representation of time zones. We could just erase all the national barriers and just put down, what time zone are you in?
Okay, I think we can start, if that's okay with everyone. So, yeah.
Okay.
Yeah, welcome everyone to Science Society, and a special welcome, of course, to Rich Spontak. Thank you so much for coming back. It's a great honor having you back again, and we are so happy that you're presenting this project today. But before we start, for people that maybe didn't hear your first talk here with us, we could um, I will give a short introduction overview. Um, Dr. Richard Spontak, he is a distinguished professor of chemical and biomedical engineering at North Carolina State University. He received his bachelor degree in chemical engineering with honors and high distinction from the Pennsylvania State University, and was later awarded the PhD degree in chemical engineering from the University of California at Berkeley. And yeah, he continued then his research as a postdoc in material science at a University of Cambridge, and condensated matter physics at the Institute for Energy and Technology in Norway. And then at some point, he joined a corporate research division of the Procter and Gamble company. And yeah, and then later on, he accepted a faculty position at the North Carolina State University, where he is still until today. And he's also an amazing teacher and mentor. So yeah, we are very honored to having you here. And Jamie will like to ask you general question before we go into your research, if that's okay with you, Rich. Thank you.
Absolutely. Thank you so much, Katerina.
Thank you, Doctor. And as anybody who's listened before, we already got your origin story from you in the past. So I thought it would be interesting to maybe ask you something a little bit different, since you're a second-time comer. Now, this question, it might have the same thing. It might be the same event or not. Let's find out.
Okay.
Do you remember the most exciting time in your career when you discovered something? And can you remember the times you were most surprised with results against your expectations? That might be the same event, it might be two different. Thank you.
Thank you for that. Though they're actually two very different events. Let me give the surprised first, because this involved my first PhD student, and at that time we were working on imaging very complex polymer morphologies, and there was a new system that we were interested in. These were actually gels, and we knew that there was a structure to them, but we just, we had to assume what it was rather than actually visualize it. Well, just so happened that I went to a conference in Russia at that time, and 2 weeks later, I came back, and he comes to my office and pops these photos on my desk. And I said, "Oh, you've got some great images of these polymer blends." And he just gave me this wily coyote smile and said, "Nope." And I looked at him. I said, "You didn't." And he said, "Yep." And he had actually gotten images of the system that we didn't think we could image, and the reason why I didn't want him to do it was because I was afraid that putting the oil containing samples into a TEM would completely foul up and contaminate the microscope, which would have meant tens of thousands of dollars in repairs. And when he showed me the images, I was both excited, surprised, and really worried. And it turned out that he was really good. He monitored everything, and it turned out that when we had the scope serviced a few months later, the service rep said that he had never seen a microscope so clean before. So even to this day, it surprises me. And whenever I see him, I always bring that up. Now, in terms of discovery, oh, that's an easy one because I'm going to be talking to you about that today. Um, this what I'm going to be showing to you was not pre-planned. It was a true discovery in the sense that we really didn't even believe our own eyes. And there's a part of me that looks back on the day when my students showed me the first results, and I said, "Okay, how did you screw up the experiment?" And he went back at least 2 dozen times with different variations to show that what he had found was in fact not a fluke, it was reality. And then the onus was on us to explain what was happening, and that's my story for today, actually. So good transition. Thank you so very much for that question. um, and yeah, I hope that answered.
Oh, that was fascinating. Thank you so much for sharing that. And that does lead us in perfectly. So thank you for setting me up properly. Okay, now we're all comfortable. We're all ready to listen. Please, Dr. Spontak, the stage is yours. Thank you.
Thank you so much. And I do recommend having the slides in front of you and put them into presentation mode, because there are some animations in there that will help you. So, and I'm going to be walking through this so that you can, I'm seeing what hopefully you're seeing. Okay. So, with that said, I'm going to be talking today about broad spectrum self disinfecting polymer surfaces. That is a mouthful. And so let me just point out the two primary considerations in just that title. Broad spectrum. I'm not talking about antibacterials here. I'm talking about antibacterial, antiviral, antifungal, basically antimicrobial. So we want to basically kill any kind of infectious microbe, any kind. Doesn't matter what it is. Now, when you go to the store and you find antibacterials, well, yes, they're focused on bacteria, and that's very specific. You don't tend to find antivirals unless you're actually taking them orally. Then you'll find antivirals, but you won't find an antiviral surface. And that's what I'm going to be showing. Now, self-disinfecting, well, this basically says that this is not a point in time solution where you clean a surface and then wait for it to become recontaminated and then clean it again. We want to have a surface that basically cleans itself all the time continuously. Okay, so though that I want to set the stage with that so that you have an idea what we're talking about. Now, of course, I have to mention people who have contributed to this from NC State, from Creighton Corporation, from Boston University, Procter and Gamble, Argonne National Lab, and the question, why do we need microbiocidals in general? Well, of course, we want to avoid spreading disease. And most people tend to think of limiting this to healthcare, where you have personal protection equipment, whether they be masks or face shields or clothing. And those are absolutely fine representations. But think about transportation. My wife and I recently came back from a trip in Europe where, yes, we were touching everything during our bouts around the cities, handrails, kiosks, seats, all of those are likely repositories of microbes that could potentially cause infection. Then you could start looking a little bit larger at just even the buildings that you're in. What about the desks that you might be sharing? What about the filtration membranes that are circulating air? What about simple doorknobs? So all of these are reasons where, or are potential venues where one could start to pick up um, an infectious microbe. Now, in the next slide, I hate to really show this because it brings back so many bad memories. This came out the end of November of 21, and it just kind of reminds us all how bad things were going in terms of the pandemic. Well, things have still continued to get bad. These are last week, and you can see that we've broken the 6 million mark in terms of deaths worldwide, uh, over 500 million cases worldwide, and yes, that number actually continues to grow. But fortunately, so does the number of vaccine doses that have been administered. So there, the problem is starting to be alleviated, but it is not disappearing. In fact, these were some shots that I got when Omicron first set its foot on the world stage. And these were coming from New York. They were sounding the alarm, saying that, we've got this new mutation. Well, now we don't just have one Omicron mutation, we have five. And more than likely, as with all coronaviruses, it will continue to mutate. It is naive to think that it is a stagnant organism. It's one of the first things you learn in biology is that organisms will adapt to their environment. And so, we wind up having all these mutations. And unfortunately, with the newest mutations of Omicron, the transmissibility has gone up significantly. In fact, this is my own COVID test from yesterday. And yes, you see that I'm still testing positive for COVID. So, is this the real scare? Well, it certainly has been a nightmare for the last couple of years, but it's not the only thing that we need to think about. I'm going to draw your attention to the next slide where you start to see lines like far greater risk than COVID. What on earth could be a far greater risk than COVID? And then all of a sudden you start to see this term antimicrobial resistance. Wait, does that mean that microbes are becoming resistant to whatever we use against them? The answer is yes. Now, this came out in September of 2020, and that sounds like this is a new thing, but it's not. This war has been waged for quite a few years, and it starts off with what are called superbugs. These are bacteria that have developed resistance against pretty much all antibiotics. So let's take a little look at that first before we start jumping back to the pandemic. So on the next slide, the initial motivation for the work I'm showing really deals with what are called hospital-acquired infections or nosocomial infections. When you're not feeling well, you go to the hospital. The hoped outcome is that you're going to feel better, but that's not a guarantee. You may find that you actually feel worse and you wind up picking up an infection in the hospital. One of the most notorious bugs that you can pick up in the hospital is what's called C. difficile. C. difficile is responsible for quite a few deaths annually in the US alone. It is considered an urgent microbe in terms of its fatality by the CDC. It accounts for about 1 billion, that's billion with a B in terms of healthcare costs. And if you're an elderly person and you wind up getting C. difficile in the hospital, chances are you're not going to walk out of the hospital. In fact, that's how my mother passed away. She went into the hospital for a diabetes-related infection. She picked up C. difficile, and within a week she had passed. So, what exactly should we be considering here? Well, let's take a look at some numbers. First of all, about 1 in 20 people who go into the hospital are going to pick up one of these infections. It might not be C. difficile, but there's a very high probability that you're going to get some kind of an infection. This accounts for at least 100,000 deaths per year in the US alone. And if you start, converting from deaths to dollars, which I really hate to do, but it gives you a little bit of insight into why healthcare is so problematic in the US. Because we're looking at about 28 to 45 billion dollars per year that deal with these types of infections. Now, I know that some of you are joining us from different time zones, and I hope I did not hit into someone's lunch or dinner with this. But these are some photos that have been obtained from an infection caused by what's called methicillin-resistant Staphylococcus aureus, otherwise known as MRSA. And you may have heard of MRSA. It is a bacterium that requires last resort antibiotics. And basically, if you contract MRSA, there is a high probability that you will wind up losing a limb, if not your life. So to put this into perspective, if you start looking at the number of infections, cases, deaths due to antibiotic-resistant bacteria and C. difficile, well, we're starting to approach a relatively large number in terms of deaths that really go unreported because they are more or less considered the norm. They are the chronic problem. COVID was an acute problem, but the chronic problem isn't going away anytime soon. In fact, if you start looking at MRSA alone, you start to see that it is pretty much widespread. And yes, we're looking at the US, we're looking at Western Europe, we're looking at Australia, South America, South Africa, and of course, all the other locations you see here. That's just MRSA. There are other antibacterial resistant bacteria out there, or antibiotic resistant bacteria out there. And the scariest part is that a study conducted in the UK indicated that by 2050, we're going to be looking at about 10 million cases of these antibiotic resistant microbes per year. That is actually going to outnumber all the cases of cancer. So this type of chronic problem is only getting worse, and it's not a matter of taking the approach that we did with the pandemic, which is let's kick the pharmaceutical companies into high gear. Let's start cranking out new antibiotics or antivirals or what have you, coming up with new vaccines. That strategy isn't going to continue to work. It's going to become inundated. And it does not account for mutation. It does not account for resistance because all of the drugs that are produced target. So they identify specific functionalities on membranes, for example, target those to basically cause disruption of whatever microbe you have. But if the microbe starts to develop a resistance against that, then the drug becomes ineffective. So, How can we combat this? Well, you can see from this chart that there are lots of different ways to combat COVID as well as other microbes. And I am really going to be focusing on materials, in particular, the charged polymers, because they're quite interesting. And as I mentioned earlier, our discovery was very surprising. Now, this is again one of those slides where it has an animation. So if you hit the button, you'll see that there's another slide embedded underneath, which is where you can start to see some potential ways in which you can kind of combat microbes. The easiest way, you use disinfecting wipes, chemicals, basically, quaternary compounds that will effectively kill whatever on the surface. Or you can use radiation, UV radiation. But both of these have their own little problems. UV radiation, of course, can hurt healthy mammalian cells, and the various chemical compounds used as disinfectants, well, they've been used so much during the pandemic that there are studies now indicating that they have adversely affected the environment. So then we can start talking about nanoparticles. Everybody loves to talk about metal nanoparticles or metal oxide nanoparticles. The copper, the silver, the zinc, the titanium dioxide. And yes, these work. But once again, they target bacteria only, and the bacteria can develop resistance to them. But even more importantly, nanoparticles like these can leach. And if they leach out and enter into the food chain, well, they can ultimately wind up in your brain. And so there is considerable concern there. One can decorate the surface, and that does work using polymers. But the problem there is that if the surface is abraded or cracks, then you wind up with regions that are not protected, and you can start to develop microbial colonies. The last one deals with charged polymers. Well, I won't say most, I'll say all charged polymers that have been studied to date have been cationic. So the reasoning for that is very simple. The charges on bacterial membranes are negative, and so if you have a positive charge, it'll actually lure the bacterium to the surface where you could have, for example, another chemical function that could act as a spear and puncture the membrane and spill out the interior of the bacterium. It's called lysing. And yes, that works. It works. A lot of times, though, these types of charged polymers, because they're wet, they have low tear strength. So they're not really mechanically robust. So we have been actually looking at two different strategies that activate when we want them to, so that they can basically inactivate microbes. Most importantly, they are non-specific. So they do not target specific chemical functionalities, and now microbes cannot develop resistance. Okay, so that's a key point. Now, the one deals with what's called photodynamic inactivation. And this is basically where one adds in a photosensitive dye that, in the presence of incoherent visible light and molecular oxygen, it can generate a reactive oxygen species, such as singlet oxygen. And this basically is highly, highly corrosive, and it will pretty much destroy uh, anything organic near it. That includes microbes, it includes polymers for that matter. But it is an approach that works. We've shown it that it works, and it's actually quite useful, especially as a coating material. But that's not the one I'm going to talk about today. The one I'm going to talk about today is our discovery, and that deals with anionic inactivation. So, what we're dealing with here is a single polymer whereby the blue regions of the polymer shown here, uh, they are hydrophobic. They provide mechanical properties and flexibility. The red is hydrophilic and basically houses sulfonic acid groups. This type of material activates in the presence of moisture. That's all. It does not need light. It does not need anything else. It just needs moisture. So, allow me to spend just a moment telling you a little bit about this polymer because in its own right, it's quite interesting. So in the next slide, and I can't tell you what slide number this is, but this actually deals with the microbial targets first. So let me tell you what we're going after, and then I'll tell you a little bit about the polymer. So I am not a microbiologist, so I kind of learned this on the fly. I never thought I would actually be getting into this area, but it's been interesting, and I have certainly learned a lot, which is always a nice thing. So in terms of bacteria, we have chosen what are called gram-positive and gram-negative bacteria. Examples of the gram-positive bacteria are shown here, whereas those that are gram-negative are shown here. Now, you might know or not know the difference between gram-positive and gram-negative, so here they are. And the thing to realize is that the gram-negative bacteria are more difficult to kill because they have an extra external membrane. And so, in general, the gram-negative bacteria are a bit more robust. Now, you'll notice that I've highlighted the first letter in several of the bacteria in red to spell out escape. The escape series, we're missing one of them, but the escape series of bacteria are the most common for producing those hospital-acquired infections. So that's why we chose these. And you'll notice that there are two there that are listed as resistant, okay? But we're also interested, of course, in viruses. So you'll see more about that in a moment as well. Okay, so the next slide, it's entitled Charged Block Polymers, and I'll just quickly tell you what these polymers are because they're quite fascinating, really. So the first thing to realize is that they form nanostructures, and these nanostructures allow for the ionic regions to become continuous. Now that's important because we want the ionic regions, the hydrophilic regions, to be continuous so that they can transport for us, okay? So this also shows that if you start off with a system where the ionic regions that appear light in this 3D TEM image are not connected, you could actually do a little bit of what we call solvent vapor annealing, which is similar to thermal annealing, where you heat something up for a period of time, but instead we keep the temperature room temperature, and we simply expose the polymer to solvent vapor, which softens up the polymer chains, reduces the glass transition temperature, allows more molecular mobility, and now the polymer can snap into an entirely different morphology over the course of just a few minutes. And this other morphology looks like this, where now the dark regions are those ionic rich regions, and you can see that they are pretty much continuous everywhere. So it's a very interesting material. We can actually teach it so that we know how much it will swell. And these materials form hydrogels, not the same hydrogels that you might be familiar with where you chemically cross-link polymers, but in this case, they're physically cross-linked. So you could take these materials, you could redissolve them, recast them, reform them, use them again, and then repeat that whole process. So we try to produce materials that are much more eco-friendly, rather than just tossing traditional hydrogels into a land waste facility. Okay, so enough of the polymer science. Now let's get to what's actually happening here. So we're looking at a couple of polymers that have different degrees of sulfonation. One is 26 mole percent, the other is 52. So obviously the one with 52 is going to have a much higher affinity for water. And I'm on the slide that says pH jump mechanism. So we're going to now see what happens when we take these films that have bugs on them, whatever bugs those might be. We're going to add water. I know it sounds funny, just add water. But when we do so, what happens is rather amazing. The surface becomes highly acidic. Why? Because the water gets into the polymer, it starts to allow for proton transfer from those sulfonic acid groups. The protons go to the surface, they drop the pH. Now let's consider just Staphylococcus aureus. We know from our own internal studies as elsewhere that below a certain pH you'll kill this bacterium. At higher pHs it'll proliferate. So that demarcation occurs somewhere between about 1.5 to 2 on a pH scale. This is where we start. If you look at, again, I just advanced the animation, so you should now see two graphs, one on top of each other. The lower one tells you that the first cycle, we're looking at a surface pH in these materials of about 0.8. So this is incredibly, dangerously, if you will, acidic. But this layer is very, very thin. It's less than 100 nanometers. So you could never feel it. But it's there. And if you start looking at how effective it is, it basically causes a 6 log unit reduction in the population of Staphylococcus aureus. Now, if you start to cycle this, you start to see that the pH starts to creep up because there are cations in phosphate buffered saline solution. But even when it has gone through 5 cycles, it still does a reasonably good job, even if the pH is at about 1.4. So now on the next slide, under pathogen testing, you could see, for example, what happens with MRSA. If we look at a time-resolved study, we find that for the material that has been highly sulfonated to 52 mole percent, it reaches its minimum detection limit. That's a 6 log unit reduction in 5 minutes. And you can see that from the live dead assay as well. Now compare this to your disinfectants, the ones that you could pick up in the store, where it says it can kill everything in 2 minutes. Okay? And that's true. It can. It gets to the same, almost the same level that we can get to in 2 minutes. But the big difference is that you have to apply it every time you want to clean that surface. Whereas in the material I'm showing you, it's continuously killing to this level. If you start looking at bacteria, whether gram-positive or gram-negative, in 5 minutes, you'll see that they're all killed to the minimum detection limit, the MTL. So now we're looking at almost complete 99.9999+ % inactivation in 5 minutes of all these bacteria. If we go to the next slide, where we start talking about the pandemic, and again, these numbers are now outdated, but it still gives you a pretty good indication that this was one of those once in a lifetime, once in a generation type of an event. But what I'm more interested in is how we can use these materials, because the SARS-CoV-2 virus can survive on plastic surfaces for 72 hours. It's 3 days. On cardboard for a day. Even on copper for 4 hours. So we have an opportunity here to make an impact. And now we can start seeing how we can actually produce materials that prevent these types of transferences, even though most of the transfer for the SARS-CoV-2 virus is respiratory in nature. So you have nano droplets, suspended water droplets from coughing, from sneezing, etc. But you can use these types of materials, for example, on face masks and face shields. So just to show that, yes, this polymer actually works really well against viruses. Here are results from 3 different viruses. VSV, which is related to rabies, influenza, and human adenovirus, which is related to the novovirus. And you can see that in all cases, it is possible to get significant inactivation of the viruses. But the moment that I think many of you have been waiting for is how well does it work against SARS-CoV-2? Well, this was some work that was done in collaboration with the National Emerging Infectious Disease Laboratory, NEDL, at Boston University. And it also shows that after 5 minutes, there's a considerable reduction in the survivability of the viruses. And it's much, much better than what you could get from using even copper. After 30 minutes, we can get to extremely high levels of inactivation. So that's comforting, because it tells us that this material can in fact be used against viruses. Well, we couldn't always be checking for SARS-CoV-2, so we went to a human coronavirus surrogate, which is human coronavirus 229 echo strain. And this is basically the strain of coronavirus that gives you a common cold. So it's safer to work with in a BSL-2 facility. The SARS-CoV-2 requires at least a BSL-3 facility. And you can see here that in all cases, we're looking at, within 20 minutes, the virus is completely killed down to minimum detection. Well, that took us back to the pandemic, but is that the end of the story? No, because that chronic problem still is around us. So what about more aggressive pathogens? And yes, there are more aggressive pathogens than SARS-CoV-2 virus. So if we go to the CDC website, you start to see the different types of threat levels and what types of bugs are responsible for those types of threats. And we're marching up. We've gone from concerning to serious. MRSA is considered serious. And the other one that I showed you results for, VRE, is also considered serious. But now we start to get back to C. difficile. And now we're looking at, between C. difficile and MRSA, you're looking at about 2.7, about $3 billion alone in healthcare costs. That's just for 2 types of infections. So, will the materials I showed you work against C. difficile? Well, C. difficile is different, because C. difficile forms a spore. And that spore basically means that it has a protective wall. So now it becomes resistant to high temperature disinfection. It's even resistant to UV light and to ethanol and bleach. Excuse me. So we did check. We did produce results from C. difficile and adhere to all the proper laboratory conditions for it because it is a bit different. It's an anaerobic bacterium. But this is what we see. So there are two different states for C. difficile. One is vegetative, where it is contagious, and the other one is the spore state, where it can stay pretty much in suspended animation for months. So we looked at two different types of C. difficile. The original one discovered in 1982, and another hypervirulent strain that was identified in 2006. In terms of the vegetative state, within 5 minutes, once again, we could kill everything down to not 6 orders of magnitude, but closer to just over 7 orders of magnitude. So considerable inactivation. The spore state was a challenge. We started to see evidence of inactivation after about 20 minutes, but we don't get to a very high level of inactivation until about an hour. So for the vegetative cells, we could actually get to 99.99% in just 1 minute. So very, very quick. For the spores, we can get to about 90% inactivation in 60 minutes. But if we model this, it basically says that if we tack on another 30 minutes, we might be getting down to that same level of 99.9+%. So with that, on my penultimate slide here, basically pointing out that these types of bacteria and viruses and other microbes, I didn't talk about fungi here, but those are also a threat. And it turns out that the polymer I showed you works quite well against black mold, which especially in the New York area, that is, and also a lot of shore areas, coastal areas, black mold is of considerable concern. And so this material actually works quite well against it. The whole point is that it produces a pH jump in the presence of water, and the exposure times are very, very short, very, very effective. I didn't point this out, but these materials are actually rechargeable, so that if cations do bind to those sulfonic acid sites, you could expose the material to an aqueous acid, and over a concentration-dependent period of time, which can be as short as just 5 minutes, you can fully recharge the materials so that they become as good as they were before. So this was a headline that I found from 2016, indicating the first superbug identified in the US. But these types of superbugs, this chronic problem, has been around for a much longer period of time. Now, the material I showed you today is quite effective against viruses such as SARS-CoV-2. And in fact, for that reason, last year, it received EPA emergency approval so that it could be used to counter the pandemic. And the reason why this was important is because this now allowed Delta Airlines to start using this material in its terminals. So if you fly Delta and you use a ticket counter or a ticket kiosk and you touch it, you're actually touching this polymer, and it is continuously disinfecting your fingers. Um, the other aspect, and I can't stress this enough, is that the way that this polymer kills is non-specific. So microbes cannot develop a resistance to it. And I'm a true nerd at heart, and so when I think of resistance, well, there's only one person who comes to mind, and that is Locutus. In terms of these materials, from a microbial standpoint, resistance is indeed futile. So, with that, I thank you so very much for the time you've given me to share our results with you. I would be delighted to answer any questions either now, or if you'd like to send me an email, I'm happy to answer any questions you might have. So thank you very much for this time.
Wow, Dr. Spontak, thank you so, so much for this talk. It's been very wonderful and interesting. Yeah, I mean, I'm pretty sure a lot of people on stage and in the audience have questions right now. And so let me see. Jamie, Gilbert, Katarina, Frank, anybody has any questions? And we have someone new on the stage. Hi.
Yeah, am I audible?
Jamie, do you have any questions?
Indeed, I do. First of all, Dr. Dr. Spontak, I'd please like to offer my deep condolences for your loss, and thank you for sharing that with us here. Um, and
I appreciate.
so yeah, and it's so meaningful that you've actually been working on such a dangerous problem. Because I'm in the UK and we've heard a lot about that as well.
Mhm.
So that being said, I'm gonna begin my questions with um, is is there actually some real plans at the moment to have this be picked up in hospitals? Am I understanding right that this is going to like coat surfaces and things? Yeah.
Yes. So uh, we have patented this discovery, and I think you can appreciate now why I was so surprised when we saw the initial results, because traditional wisdom said that the polymer had to be cationic. No one had ever suspected that an anionic polymer could be used. And in fact, I even wrote to one of my dear colleagues who is an expert in biomaterials, and I explained the situation. And I loved his response. It was just two words: patented. and yeah, it was a surprise for us. But now the question becomes, how does it move forward? So we have licensed this technology to, this is the ironic part, to the company that manufactures it. So we were using the same material for vastly different purposes. We've used the material to create electroactive media. We have used that polymer to make solar cells. We have used it to make gas separation membranes, although I didn't talk about that during my last talk. We have now recently filed a patent where we can show that we can make lithium ion batteries that can retain 100% efficiency and 76% capacity after 1,000 hours, or 1,000 cycles rather, which amounts to about 4 years of service. So the material itself has been incredibly valuable because it forms these nanoscale hydrophilic channels. That's really important. It is one of the very first polymers where you can see the importance of how this that charged midblock plays a role. So now it's basically up to Kraton Corporation how it will be distributed. And I know that they have been in discussions with hospitals. In fact, even when we first made the discovery, we were being contacted by Massachusetts General Hospital um, about how we could apply this as a coating onto a surface. It turns out that the best way of doing this is what's called a peel and stick, where you basically have um, an adhesive onto a non-woven backing and then put this polymer on top of it. And that works really well. So you just peel off the adhesive, stick it onto the surface, and away you go. And you could do this on walls. Um, it's not as simple as wallpaper, but it's not that much more difficult. And the nice thing is that our current results indicate that even if you apply disinfectants to it, you can still recharge it and it will get back to its full efficacy. So, um, I'm hopeful that, Kraton will take this into all the markets where it needs to go. Um, I think the thing that complicates matters a little bit is that Kraton was just bought out by a company in South Korea. And so I don't know what the long-term strategy is for that parent company now. But this material has tremendous potential. And one of the reasons why I was so personally excited about this was that it can be used in economically hard hit areas. So you could start thinking about even mobile hospitals having this kind of polymer coated onto surfaces. Um, it's actually we can take this material, dissolve it in a solvent, and spray it onto a surface, and it works. It works quite well. Um, so I think that, from my standpoint, I would really like this to be used, not just in our hospitals in, the more industrialized nations. I would like to see it used in developing countries where, there's still issues associated with Ebola, for example. One of my goals this year is to see whether or not we can kill a number of those types of hemorrhagic fever causing um, microbes with this material. So, yeah, it still has a lot of potential in terms of where it can go, um, but how it gets there is not exactly in my hands anymore. Does that make sense?
Oh, most definitely. And thank you very much for answering. It's, an, it's a jaw-dropping discovery, and I'm itching for it to be everywhere right now. Thank you very much. I'll yield the floor, but if there's any time, I'll have more questions later. Thank you, Doctor.
Well, that was your description is actually quite right. Jaw dropping is the right description for that because um, it took us a long time to believe our own results. And when we did the first COVID tests, uh, we actually had two other labs follow up on that to make sure that we weren't getting spurious results. And the other labs showed almost identical results. In fact, even slightly better results than the results we got from Boston University. So, yeah, it was quite eye opening. And when we saw that we could now also kill C. difficile, that was just mind boggling. Because even our collaborator, who is an expert with C. difficile, she said she had never seen anything kill the spore form so quickly. And I was like, quickly? That took an hour. And she said, you don't understand. The spore form of C. difficile is extremely difficult to kill. And so, yeah, I'm hopeful that this can make it into hospitals. Um, and also nursing homes. It's another place where these microbes can really have a major deleterious effect against the seniors who are more or less confined to those facilities.
Oh, wow. Oh, go ahead. Sorry, Katarina.
Yeah, thank you so much. This is really amazing, and I the whole time I was wondering, because it is really so effective, and so the results are really so astonishing. Would there be a way to package this and deliver it in an organism in a body so that it would only be released? Like, is there any work in the future for that, for antibiotic resistant
Yeah,
microbes?
you kind of hit on the Achilles heel because this material is cytotoxic, so it will kill live mammalian cells just as easily as it will kill bacteria and viruses. Um, we checked on that. It's not as fast, but one of the first things that we thought of for using this, excuse me, uh, for wound dressing. And we thought, oh, this is perfect because you don't need light, you don't need any kind of special stimulation. All you need is natural water, which occurs, either from the wound itself or from irrigation. But no, we found that because it forms that thin acidic layer, it still kills cells, healthy cells. The other thing that you kind of have to think about a little bit is, as I mentioned earlier, the composition of the polymer. It has T-butylstyrene end blocks, and those are really important because they act as physical crosslinks. So that's why when this material soaks up water, and it can, under the right conditions, it can soak up almost 1,000% water. So it becomes ultra absorbent. But it still stays intact, and that's because you have these physical crosslinks. So when I said it behaves like a hydrogel, it does, but it's not chemically cross-linked, it's physically cross-linked. Well, styrene, unfortunately, is one of those chemical compounds that the FDA has not approved for internal use. And the reason for that is because when you synthesize a polystyrene, um, you always invariably have some styrene monomer or styrene oligomer left. And that could easily get into the bloodstream, which styrene having that lovely phenyl ring on it uh, can produce cancer. So there is, at least in the US, there is, um, you know, a major dislike of putting polystyrene in the body. Now, in other countries, it's actually allowed. I was surprised to learn that, I believe it's in Japan, you can in fact put polystyrene in the body, but not in the US currently. Um, it's possible to switch that out to a different polymer, but now you're also talking about all of the development and capital costs associated with changing the polymerization process. That's not trivial. That could be millions, tens of millions of dollars. Um, so I think that as of now, I think all of the intentions for this polymer are external to the body. Um, but a person once asked me, if I'm suffering from a MRSA infection, um, you know, could I get this material because it could kill the MRSA? And I said, yeah, but it's also going to kill your healthy cells. And he said, I would rather lose some cells than lose my leg. And that's a fair point. But you know, I can't I cannot authorize that kind of use. Uh, but I think it really depends. There are some situations where it could still potentially be used uh, directly in conjunction with the body, but you know, uh, all of the potential issues must be considered. So, but it's a good question. I've been asked that question before about using it in the body, and I'm very reluctant to say even a potential yes, uh, especially since this is driven. This is a surface-driven phenomenon. So, um, if you had this introduced into the body, basically you would have uh, a sphere with a highly acidic surface, and I'm not sure exactly what the benefit would be there. But again, there's a chemical concern that has to be addressed before that could happen.
Yeah, thank you so much for that answer. I was thinking of the guest speaker here from Japan last week, where he has this micro robots that he can program with DNA and then have one type of light pack up stuff and then UV light to deliver like compounds. Um, but yeah, then you have the light issue and to target it.
Well, but that's the
Probably
nice
just
thing. Yeah, with these materials, you don't need light, right? All you need is water.
yeah, that's much better. Yeah, thank you. I see Frank had the question.
Oh yeah, yeah, yeah. Thank you, doctor. This is fascinating. Thanks for sharing. It's an exciting finding, and I already can see that the with the huge potential huge impact on the especially the during these after this affliction of pandemic years and stuff. Yeah, so this is really interesting, especially it's in the nano science. I worked with a polymer on the more higher level. It's more engineering with 3D
Mm-hmm.
printing, but yeah. So, but I do have a question related to the slides of the charged block polymers. I just try to understand better of what type of this type of block polymer, and as I understand the itself already with the ABA type of built in, and so you can I do see a word in this slide that it's irreversible. Is that a typo, or because by from earlier you were answering Karina question that the difference between chemical versus physical, in my mind, if I'm correct, that correct me if I'm wrong, that the physical ones is you can still reuse
Right.
instead of like a rubber, you become fixed.
Right. Which slide are you referring to?
Charged block polymers,
Oh, okay. Let me.
AAI.
Yeah. Yeah. Okay. Let me. Uh, Okay. So typically, with block polymers, you can change from one morphology to another if they're equilibrium morphologies. Okay, so a good example of that is if you don't have a charge and you're dealing with an AB or an ABA type block polymer, and these will spontaneously form into a number of different morphologies, which I didn't get into in this presentation, but those are equilibrium morphologies, and so you can easily switch from one to another by crossing what are called order transitions. And so you can go from spheres to cylinders, cylinders to gyroid, gyroid to lamellae. That's all very doable, and it's been shown ad nauseum times. No, what this material does is if you start off with that micellar morphology that is in that slide and it's rotating, it's a three-dimensional TEM image. If you take that and you expose it to a polar solvent like water, okay, what will happen is you'll have a buildup in osmotic pressure within those hydrophilic channels, and it will undergo a transition to a different morphology. That morphology is very disordered. Um, there's no long range order to it, but the ionic channels become continuous. That transition is irreversible. That is, you cannot now just take water away and it will go back. It will, that new morphology stays. Now you can redissolve the polymer, but I'm just saying that that transition is irreversible, not the fact that you can just redissolve the polymer and reuse it. Okay, do you see the distinction there?
I see. I got okay. So
Yeah, you're absolutely
yeah.
right, though, because that's one of the beautiful things about these types of materials. This, by the way, is a pentablock, so it has 5 blocks to it. And the beautiful thing about these types of materials is that they are recyclable, they're reusable and reprocessable. So it gets all those little re's in there, which makes it much more of an eco-friendly type material. So you're absolutely right about that. But this irreversible only refers to the transition itself.
I see. This is a really great great material. Really
It
great findings as well. Yeah.
and if you send me an email, I'll be happy to send you a full listing. We have probably I want to say about 30 papers out on this material. I'd be happy to send you the list if you're interested in learning more about it.
Yes, yes. I'll do. Yeah, really appreciate that. I'll shoot an email to you
It'd be
soon.
my
Yeah.
pleasure.
Yeah, it's so quickly, if I may, additional. So as you were explaining earlier, I'm trying to get so so this polymer can be in a spray form. So what is the chain size, the molecular weight? I mean, how long is you can,
Yeah, the molecular weight is
or you
not.
can develop into like fibers of a long chain? Or what morphology is
Uh,
most preferred?
Fibers are going to be problematic. So here are some of the things that you need to think about. One, uh, molecular weight total is on the in the ballpark of about 80,000 Daltons, 80,000 grams per mole. So it's not a high molecular weight material. Um, the the end blocks are actually just below the critical chain length of entanglement for T-butylstyrene. So you have to be a bit careful with this material. It's not as mechanically stable as I would like. I've taken this material and I've added in homopolymer to try to strengthen the end blocks a little bit. Um, but so it's on the relatively lower side, which is good from a viscosity standpoint because you can actually work at surprisingly high solution concentrations before it starts to gel. Um, but in terms of fibers, the sulfonic, if you're thinking of fiber spinning from using conventional thermal melt spinning, you're going to have real problems because the sulfonic acid group will degrade. It starts to degrade at about 60 to 70 degrees centigrade. So from a melt spinning process standpoint, no, this material cannot be spun into fibers. We have spun it into fibers using electrospinning at room temperature. That works. but if you're familiar with electrospinning, you're not going to get much out. So the one thing that we have considered is electrospinning on top of um, a fibrous support, so that you basically just fill in the pores. But it's not something that you could think about as large scale. Um, this is actually much better suited towards uh, solution casting, solution spraying.
I see. Gotcha. Yeah. So I think the people, I'll reframe, my questions. I'll leave have others to ask more questions. But I do have so if we still have more time, I would really appreciate you
Sure.
explain, repeat, spend a little bit more time on the explaining the morphology. I mean, I missed some of your words description as you go through this particular slides. How the A B, but I can wait for later if there's more time
Certainly.
available.
Yeah, we have a good friend on stage, and I kind of wanted them to get their question in, just because we don't know how long Dr. Spontak has. Good friend, hi.
I am not planning on going anywhere. I have
Yeah, I want to say
I'm for Frank
all the
or
best to Dr. Spontak. Very interesting one.
Oh, thank you, Dr. Spontak. Yeah.
and I like the music there too.
that was good. He has some background noise. He usually asks great questions, but I know he has some background noise today. Good. Can you ask your question really quick?
Sure.
Yeah, I was just saying that the question that I was willing to ask, Katrina already asked. So I'm just thanking Doctor for his this wonderful work that I can spend a week, talking to people about it. So great learning for me. Thank you.
Oh, okay, okay. I think they're saying that the question's already been asked. Okay. Well, that's great.
Yeah, yeah, yeah.
Okay.
Okay.
Yes.
Um,
I'm having a hard time making out the comment over the music, but the music actually was quite nice.
yeah, no, definitely. Gilbert, you're the only one who hasn't asked yet. I want to know if you have any questions.
Hello, can you hear me?
Yes, clearly.
Yes.
Yes.
Perfect, perfect. Thank you very much, Doctor, for this great topic. It's an excellent topic. I just
Thank you.
had one question about the polymer itself. Is there a way to actually make it safer for external use as well? Because I mean, if we plan on using it on surfaces, on various different types of surfaces, or in specific places that where it's effective, there's no guarantee that we can actually stop it from entering the body, because particles, they're everywhere, and people are touching everything all the time. So how can we actually make it safer for external use and prevent it from actually entering the body?
That's an excellent question. So we have been talking with people who make face masks to try to apply this as a coating on the face mask. It can be easily applied to face shields. So basically, bringing it closer to those portals to the body that would be the entrance for infective microbes. So you have to start thinking about, of course, the nose, the mouth, the eyes, the ears. All of these are entry routes. And so if we can basically manufacture PPE that has this polymer on it, and then use the PPE to basically bring our polymer closer to those entry ways, then I think it becomes more effective in combating the uh, the infection, basically trying to prevent the infection from occurring in the first point. So it's a good question, and actually, we have been working with colleagues over at Duke University. They have built essentially a chamber that emulates a cough or sneeze. And the idea is to use laser interferometry to measure particle size as a function of distance and of speed. And so that gives us a better indication of, what should we be doing in terms of modifying PPE so that it can be more effective at preventing the risk of infection. So I would say we don't necessarily have to do anything to the polymer itself, um, other than ensuring that it doesn't delaminate from whatever the uh, underlying polymer substrate is. So most face masks, for example, are made from polypropylene. Which means that if we want to put this polymer on polypropylene, we have to make sure that it won't come off easily. And there are ways, chemically, there are ways to improve that adhesion. But that's the type of problem that, you know, develops. It's not so much in modifying our polymer per se, it's in modifying its adhesion to other polymers that are used in PPE. Does that make sense?
Makes perfect sense. Thank you very much.
You are very welcome. Thank you for the question.
Yeah, thank you so much, Dr. Spontak, for answering all of our questions. So I just had one more question for you, and I think maybe a couple more people. Jamie and Frank had maybe one or one each more that we could ask. But for my question, I wanted to ask because I love that you mentioned the use in low-income countries and lick mix around the world, and you were talking about the company that has taken over the production. So right now, my biggest concern, if you're, talking about use of it in licks and mix around, expensive is it to create, and how expensive is it to maybe sell to these countries that might really need it? Healthcare. And if there is some sort of healthcare facility, it's not safe, it's not, sterile, it's not, cleaning up. So yeah, so how much does it cost to create? And is it really difficult? Like, does it put a burden on any kind of infrastructure? You know what I mean? Like, does it really fit into the low income country kind of budget and infrastructure?
Uh, I'm going to answer that question on several levels. Um, the first one is the polymer itself and how expensive it is. Um, as far as polymers go, it's not as cheap as, for example, polyethylene or polypropylene. Okay, those are incredibly cheap. That's why you get them all the time when you go to the supermarket. Um, but this isn't as expensive as some of the more high performance engineering polymers. So I would say that the cost is not excessively high, but the good thing is you don't need much. So you don't need to have a block of this material. If you have a film that is 100 microns thick, it will work. So that's kind of the beauty of it. You don't need to have much of it. So that's going to reduce the cost tremendously. Okay. Right now, the process is industrialized. It is a commercially available polymer. You can look it up. It's called Biaxam, Biaxam, and you'll see Kraton's website that says it's a wonderful thing for killing microbes. um, but it's more a matter of how they want to distribute it. Um, and I know that they actually have quite a large warehouse of this material. And again, it's typically sold in sheet form. So the sheets themselves are a bit on the thicker side so that they can be handled, but they can be redissolved and made into thinner coatings if necessary. So, I think that to answer the first part of your question, yes, I think that it could be used in economically hard hit areas without introducing a substantially unnecessary burden on the healthcare system. That was the intention. We wanted something that we thought would be relatively inexpensive and accessible. How that pans out from an industrial standpoint, I can't say. I don't have any say in that whatsoever. Now, the second level to answering your question, and I personally find this one to be the most intriguing, is that we've identified a brand new mechanism for an antimicrobial. It, prior to our work, no one had ever used an anionic polymer for this purpose. We have since other polymers that could potentially be used as an anionic material, and we have that they work. So our mechanism, and that's where I come in as a polymer scientist. I look for mechanisms. I look for generality. Not just will it work for just one material? No, no, no. I want to find the works there so I can transplant it to different places. And so now I have a mechanism that I can track, and I have already submitted proposals that could potentially take other cheap polymers, very, very cheap polymers, and functionalize them so that they could have the same um, potential, the same property as these I've talked about. So, from my standpoint as a polymer scientist, knowing this mechanism exists allows me to now expand it and to see how it could be used in an even more ubiquitous way. So, that's where I'm coming from, and I really, I mean, from my last talk, I hope you got the sense that I really care about uh, cleaning up CO2 from the environment. This is my other holy grail, which is trying to make the world a safer place in terms of, fighting microbes. So, I mean, if I'm Don Quixote, I've got two lances. These are the two areas that I have particularly decided to specialize in.
Yeah, no, thank you so much for sharing that. I appreciate you talking about, all the layers that go into it. Yeah, and yes, your passion does come through, and it's always nice when you meet a scientist that is very passionate about what they do beyond just the science of it, but also how it applies to the human population. So thank you so much for that. So we have someone new on stage, Brandon. Hi, Brandon. Do you have any specific question?
Hello. Yes.
Yeah, Brandon has
Yes.
a lot of good questions in the chat. So yeah, I thought probably great
Oh, I'm sorry,
to
I
have
don't
him
have
ask.
my chat up. How do I get to chat on?
Oh, no, no, no. You don't worry about it. We will handle that for
Oh,
you. So, yeah. Yeah, that's why Frank brought, Brandon up. So don't worry about that. Brandon, please ask your question.
Thank you. I appreciate it. And Frank, thank you for having me on stage. Let's see. So I had a variety of questions. I don't know if I should get to all of these. Um,
Um, like
I was
some of
curious.
your questions
Go ahead.
were asked. I think Katarina asked the one about, the skin, and some of the people might have asked some of the questions that you were talking about. But maybe start with one for now.
Okay, sure. So on the idea of, well, there's two that kind of go hand in hand. It seems as if you were saying that this this isn't intended for ingestion, and there are concerns about that. And so then the question that I have is, I mean, as I'm sure that most of us are aware, when you smell something physically, the particles actually touched your nose, and so um, there's a variety of there's a small degree that can essentially detach. And I know that you mentioned an adhesive, and so when you said adhesive, I thought that this would be applied on one side, and so in my mind, that means that there is still a width of which it does not have this adhesive. And I'm wondering, I can imagine potential scenarios like we just went through a pandemic and we had a variety of, you could say, PPE that was not only worn by professionals who were properly trained, but also by individuals who, they were not properly trained. And so I think of a scenario where, this could potentially uh, it could evolve where this application is used in one setting and then it's pushed towards the public, and then perhaps people with PPE wearing masks multiple days, just throwing it around in their car or whatever. People can scratch the thing, etc. And so I'm wondering, potentially, you know, if it does get ingested, what may result? And so I'm trying to counter. I think that there are some potentially fantastic applications here, and I'm also trying to counterweigh that on potential risks. And so I'm sorry if that was too all over the place, but
No,
I am
I,
curious.
I followed you, and um, I assure you that I devil's advocate so many times with this material because we do not want to introduce unnecessary risk to any user. That would be the farthest thing from our intention. So um, yes, if you want to get straight to the bottom line of, gee, what if some kid decides to take a nibble out of um, one of the coatings, that's on a Delta plane, for example. And we have considered that, by the way. When we were talking with Delta, we even asked the question: is there a chance that a child could lick this material from, an armrest, or actually take a little bite out of it from a coated seat? And yeah, these are possibilities. Now, what effect would it have? Probably nothing. There would be so little of it. Um, I mean, you can ingest a piece of poly. I recommend this, by the way. Please don't get the wrong impression. I'm not saying that you should go out and start, chewing on polystyrene, but people have ingested polystyrene, whether it's from a styrofoam cup or any kind of, children have, in addition to putting things up their nose, I'm sure that they have swallowed polystyrene at some point in their life. It's a very, very common polymer. Um, and so nothing really is going to happen. The reason why we are particularly careful about internal use is in this long term, then there is the potential for, since it is a monomer is known to be cancer causing, there is the potential that it could be cancer causing in oligomeric form, probably not in polymer form, but when you still have some leftover monomer and some oligomers, short chain polymers that could come out. And so it's not, if it happened once or twice or half dozen times or even more, it may have absolutely zero effect. It would be basically excreted. There would be no harmful ramifications. If it were used continuously, that's a different story. But when it comes to any with any kind of medical treatment to the body, I am not a physician. I am not qualified to make those types of decisions. I am extremely conservative, and so I, simply say that I cannot recommend the use for internal purposes, but it doesn't, in my mind at least. And again, I have no toxicological data to support this, but in my mind, I don't see where having someone ingesting um, you know in a discrete number of times where that would cause a significant and long-term problem. But again, I have to always put a disclaimer. I don't know for sure.
Thank you. I really appreciate that. And if I may, the only follow-up points that I'd take into consideration is, and I'm a layman, so I read some things and I don't know exactly. So I have heard over the years that there's something called a shift space, and it may be the case that certain man-made particles that we did not evolve with may not be so easily excreted through
Oh yeah.
through our feces and urine. Perhaps sweating may help out in those instances, but so that's kind of a concern I have. Is I would want to know how this particular chemical structure relates to kind of natural structures, and if it can form that, I think it's called shift base. And also, you mentioned the nanoparticle angle, and so I'm sitting here thinking, persistent plus potential nanoparticle, getting in to cells or perhaps disrupting blood-brain barrier, or who knows what, getting into the brain and alternative mechanisms. Might it be the case that this is, I don't know, like I also think of kind of like very low dose, but perhaps potentially staying. And then you mentioned like a persistent action, and I'm like, ooh, that kind of sounds like a, I don't know, alpha particle like decay that maybe it seems to do nothing for X amount of years, and then perhaps cancer shows up at some point. So just some further thoughts. Thank you.
No, that's really a good point, and that's you actually why we opted to avoid nanoparticles for exactly that reason. We don't want that to happen, and the materials is we don't produce them in nanoparticle form. They are produced strictly in terms of our coatings on other substrates, but they don't form nanoparticles. So these types of materials, they won't, within the body, they simply won't start to form nanoparticles on their own. So I would say the chance of them getting into cells would be extremely, extremely low unless you particularly put them in contact with cells that could be damaged, and don't know exactly how that would proceed. But I can't imagine, if you ingested this, I don't see any way that it would make its way out of the digestive system, because after all, they are plastics. The nanoparticles, those are metal or metal oxide, and they can easily, because they're inherently hydrophilic, they can inherently get into cells. That's very well known. But I don't think that's so much of an issue for this polymer, especially since it doesn't particle form. We're not trying to produce micelles, for example. We want it actually as a bulk film. So yeah, but good. Your point is well taken. I don't think this is going to be one of those cases where, if you ingest it, it'll come back to bite you. 5 or 10 years into the future. I just don't see that happening. But again, I'm not medically qualified, so I'll have to, recognize my limitations on that one.
Thank you for the
Thank you.
clarification. I must have misheard regarding the nanoparticles. Thank you.
Yeah, thank you so much, Dr. Spontak, for answering all these questions. I think maybe we could take one or two more questions. Yeah, Frank has a question. Jamie, did you have a question as well? Jamie?
Yes, I did, but I'm totally happy letting Frank go first, and then I'll ask
Okay.
mine. Thank you.
All right. Well, Frank, please ask one question, and then Jamie can ask another one.
Sure. Thanks, Sarah and Jamie. So quick question regarding the percentage of sulfation. Is 52 the somehow is there a specific reason that
So
is it the maximum that you can do, or
no,
is it
not at all.
what if you go higher?
It is possible to go higher, and we have. So commercially, that's the highest. The 52 mole percent to 2 equivalents. So commercially, it's available at 1, 1.5, and 2 equivalents, 6, 37, and 52 mole percent. Now we have, and I didn't, we have a lot more data dealing with this subject, but we actually have synthesized our own materials in-house, and we have gone to sulfonation levels. It turns out, though, that killing everything in 5 is what we get. So we haven't done the kinetic study for all sulfonation levels. We could do it with something simple like Staphylococcus aureus, but our initial point was to try to look at how generally applicable is this approach. To look at as the title showed, a broad spectrum. So that's the goal. But yes, we could start to look at variations in the kinetics of inactivation based on different sulfonation levels. And my suspicion is that we're looking at changes on the order of or even below minutes. So I don't know if those studies would be terribly, terribly meaningful from an application standpoint. Okay. But yeah, in principle, we could actually take the commercial materials and sulfonate them further. It just means that the material will want to swell more in water, which means that there's more stress buildup on those end blocks that act as physical crosslinks. And the more swelling that occurs, and the more stress on those, the weaker the material will become. So get to those low tear strength materials that are usually indicative of the chemical hydrogels.
I see. Thank you. So, since you mentioned the percentage, I mean that you can do in lab. So quickly on the slides I mentioned earlier. So you have that figure, the TM or SEM A and B. So I only see that the the reference bar is the resolution is different. One is lower, one's higher.
Oh,
So what are the story? What is the?
sure.
I do see an interesting pattern, and the one A is seems to
Yeah,
be just random, and the other one is somehow
it's much
has a
more ordered.
pattern.
Yeah. So it's actually the first line in that in the, it says that the material is solvent templatable. So what happens is, and these, by the way, are 3D images. So it's a technique that we actually pioneered in my lab many years ago. Um, and the reason why they're different is because we use different solvents. So in the case of A, we use solvent composed of toluene and isopropanol. I believe it was 85% toluene, 15% isopropanol. And what that gives you are ionic micelles. So the white areas that you see there are the ionic microdomains, and they're embedded in a hydrophobic matrix. Okay. If we in B and we go and use tetrahydrofuran, which is a single solvent, but it is slightly polar as an organic solvent, we get a combination of cylinders, which you see in the lower right. We also have lamellae, which are those kind of stripes, the bilayers. It turns out that from a standpoint, the lamellae actually turns out to be the thermodynamically stable material. But because of the different solvents that are used, we can actually change the micelles that you see at top to the combination of cylinders and lamellae that you see in the bottom. The reason why the scale marker is different is just to show more detail of the micelles because they're smaller than the other structures, and it's the only reason why there's a change in scale. But same material, just different solvent processing. That's all.
I see. Interesting. This is a very interesting material. Yeah.
Oh, it is.
Looking
Yeah.
forward to know more. Yeah. I'll give back the mic to Sarah.
Yeah, no, Jamie. I just wanted Jamie to have the chance to ask this question because I know he has another one.
Only one. That's funny, Cecilia. I actually, so I won't take up too much of your time, but first of all, I want to say again, honestly, Dr. Spontak, you are nothing like Don Quixote. Your goals have been much more achievable, even though they are, yeah, also impressive. There's no windmills for you, sir. Um,
Well,
but
I guess I have to
so
stop.
second,
I guess I have to stop building the windmill in my backyard then.
no, keep it. It's energy efficient, yeah. um, Okay, so my questions here is one is there any issues with this process in any way about microbes adapting to anything like this in the future? And connecting this to that, could this self-sterilizing polymer be used in medical equipment? I was thinking like bandages and plasters when people are like out and about in places that might be prone to having these kind of things, not on the inside, but on the the outside, so that the plaster protects from any extra things going on. Thank you very much.
Okay, good questions. So the first time I presented this at a biomedical center in Poland, this fellow gets up in a huff at the end of my presentation. You're going to be creating the next um, evolution of Frankenstein microbes. I was just like, okay, how do I respond to that? But it's your question hits right at that matter, right on the pinpoint there, because microbes cannot develop resistance to a general type of stimulation like this. Um, all the drugs that have been developed, even the ones for V2, they all target. And so that's where problems arise with regard to resistance. This is, our materials, if you want to think of it in a very crude way, this is like dropping them into an acid, you know. And yes, some microbes are acid resistant, but it's the pH, it's the sudden change in pH that can cause the death of the microbe. And so that's why even some of the microbes we looked at, they're inherently acid resistant. Even the human coronavirus 2 strain, that turns out to be more acid resistant than SARS-CoV-2, even though they're very structurally. But it's that sudden change in pH, really, really kills. And even if it takes 20 minutes rather than 5 minutes, it's still quite effective. So I'm not overly concerned about microbes developing a resistance to this, especially since it is, once it becomes more and more generic and widespread in terms of use, there's always a possibility, but I just don't see how, because it doesn't mean that, okay, it has to develop a new protein strand, it needs to develop a new part on the membrane. It won't matter. So that's why I don't think that a microbe can develop resistance. Now, maybe I'll come back in a few hundred years and say, oops, I didn't think about that. I just don't see it happening right now. And again, I'll point out I'm not a microbiologist, so I can't, 100% certainty. But I can say that to the best of my knowledge as a scientist, I don't see any way that it can. And I have been proven wrong before, so it wouldn't be the first time. Then to answer the second part of your question, can these be used on bandages and so forth to prevent occurrence from maybe getting into a wound? Yes, actually they can. So as long as the polymer does contact with skin. So if you have a bandage on something and you put this polymer on the outside of the bandage, it will work fine. There will be no problem whatsoever. And so, yes, there are applications for, but not direct wound dressings. These would be more indirect, but they would function quite well. And so, yes, it could be used for that purpose. So, good point. I really hadn't thought much about that.
Thank you very much for answering my questions, Doctor. And I may be reaching out for those journals you've promised before. So thank you very much for your time.
Pleasure. Just drop me an email. I'm happy to.
Thank you very much. And thank you for being out there doing all this work and for talking to us today. Thank you. That's me. That's me for the night.
It's been my pleasure. I really enjoy talking with you all, and what you've done with this idea of the Science Society, I think is absolutely brilliant.
Well, thank you so much, Rich. That's great to hear. Thank you so much for sharing your wonderful research here. And I wanted to support, what you said, that since these polymers attack membrane surfaces, it's not it's highly unlikely that they can somehow change DNA structure, since they kind of basically dissolve the membrane, and the rest will just dissolve. I don't think there will be any concerns of changing the DNA. It's just cell death, but that's what we want to kill the germs on surfaces. So I think this is such a great and especially the part you said that you were developing now, very affordable polymers. to achieve this is really wonderful, because in many places around the world, well, and even in our countries, to be priced, have a low price is really important for many different cities, parts of cities, and applications where people maybe don't have so much money. So I think that's another very important work you're doing, and I applaud you for that. So yeah, thank you so much for being for doing the work that you do, and for being here explaining it to us. And yeah, please continue, have all the funding, and you probably do have anyways, but we still wish you, well, and that you continue your very impactful research, and yeah, that everything works out wonderfully for you and your lab. Thank you.
Appreciate it very much, and again, glad to be of service.
Yeah, thank you again for
Thank you,
everything.
Rich.
And thank you everyone on stage for adding to this, wonderful conversation. And the people in the audience who also posted in the chat, thank you so much for making this, the whole experience really amazing. The typical science society experience. So yeah, I guess we're shutting down the, I'm sorry. I guess we're shutting down the room now, right? We're turning things down. I guess a couple of announcements. Oh, sorry. Did you have something to say? Oh, never mind.
No,
um, yeah, a couple of
Some
announcements.
infections, doctor, or what?
I'm sorry?
No, no, I'm just kidding. That whether doctor is facing some cold or cough infection or what?
yeah, I've got COVID right now.
Oh no. Oh, well, I hope you feel better soon.
Thank you.
Yeah. Um, so we have on July 11th, Dr. Shen coming in, talking about continuous Bose-Einstein condensation. And also the same day, later on in the day, we have the author, Howard Bloom, talking about global brain, which is actually a book. So this is going to be really interesting. So yeah, please stay tuned for that and many other rooms that are coming up in the Science Society. Yeah, so that's all I just wanted to say. Thank you all for this great room. Thank you, Dr. Spontak, for coming back. And, if you have time, please come back again and spend time with us, because we really do enjoy your time here with us. So, yeah, we're just going to close down the room. Katarina, do you have anything last thing to say before I close?
Oh no, thank you so much, Cecilia. And yeah, thanks. Follow the club if you like discussions like this. Thank you, Rich. And again, you're always welcome to come back and share at any time. And we hope you feel better soon. And thank you for making it nevertheless. Thank you so much.
Thank you. I appreciate all the sentiments, and again, it's my.
All right. So, yeah, we will be closing down the room in 5, 4,
Okay. Bye,
3,
everybody.
Bye.
Bye bye.
1.
Bye,
Bye.
everyone.